feel slightly wary following Edward's really impactful and engaging talk with my little spiel. But I would like to thank Edward again. So inspiring to see the incredible work you're doing and the benefit it can have on humanity. Lots for our team to learn from. So I'm going to talk a little bit about embodied carbon, and that's one of the streams of our high performance architecture team. I'll be followed by some of my more learned colleagues talking about their research as well. And I think I'd start with, the angle which I usually start with, which is to build is a fundamental societal good. We need to build. The United Nations suggests we need to build adequate housing for 3 billion more people by 2030. 7 years. Globally, we are urbanizing, the populations are increasing, and 1.2 million people live in slums. So we have a moral and ethical need to build. There's not much better we can do for people than to build housing, to build hospitals, to build schools. There's a picture of Dharavi in Mumbai I took about 12 years ago. The flip side of that is building is a societal good, but building is fundamentally an environmental bad. You cannot build without an impact on the environment. Every square meter we build has an impact on the environment, and the vast majority of times it's a negative impact on the environment. So these stats you all know, I'm sure you've all heard them. Our buildings are responsible for around 37% of energy and process-related CO2 emissions. Something like the cement industry, which we all rely on, is responsible for 8% of emissions. You compare that to the much maligned aviation industry, it's about 2.5%. And the process of building, the process of creating our built environments, is fundamentally changing nature. This is an incredible statistic. I always find that if you weigh all our buildings and infrastructure, they now weigh more than nature. We are truly in the Anthropocene. We have now dominated nature, not in a good way, even. So what can we do about this? This is part of what the research myself and some of my colleagues are looking at. If you measure the greenhouse gas emissions from buildings, they actually take place across what we call a life cycle. And again, you've all seen diagrams of this from cradle to grave. So if we were to create this building now, the kind of the steel here would probably be mined from iron ore. It would be transported to a factory. These would be manufactured. They'd be transported to site. They'd be installed. There's emissions at all those levels. Then the building opens. We start to air condition it. Then we get more greenhouse gas emissions. Then in 50, 100 years' time, hopefully 100 years' time, we knock this building down, demolish the building. That contributes to greenhouse gas emissions. And all that's documented in this kind of diagram. The only part of that process we regulate and consistently measure is that one, the operations. And it's only really in the past kind of 10 years or so we've started measuring all the other bits and pieces. And that's part of the research I'm involved in. Will is digging away at on a daily basis as well, looking at how we measure this and how we reduce it. So what is embodied carbon? Again, I'm probably preaching to the converted, you all know, but as a kind of headline, it's greenhouse gases related to the materials of construction. And then you've got operating carbon, which is the greenhouse gases related to the day-to-day operation, the lighting, the heating, the cooling, the ventilation. And at a pretty basic scientific level, if you add the two together, you can measure a building's total contribution to the environment. It's life cycle carbon. You go back 10 years, most of the data suggested that 80% of emissions were in operating and 20% were in embodied. So we had this kind of, this is my attempt at animation, by the way, this kind of graphic. And this is why we regulate, energy efficiency. It's why we have building regulations, because we thought, historically anyway, the vast majority of our environmental contribution is in how we operate buildings. Well, we've started decarbonising electricity. We've got better energy efficiency. We've got more efficient buildings. And so when we measure this now, we typically find it's about 50-50. You create a new building in Australia today, across its life cycle, we anticipate about 50% of its emissions will be materials and construction, and 50% will be the energy to heat and cool the building. But that's changing as well. And actually, there's an ambition in the Australian built environment, now building regulations, to move to net zero operating. So all being well, by 2030, the NCC, National Construction Code, will mandate net zero operating buildings. It's a good thing. But it also means that the carbon profile of our buildings will change dramatically. It means 100% of emissions will be embodied. That's a massive psychological shift. We've gone from embodied carbon being something we don't measure at all, very rarely, about 20%, to embodied carbon potentially being 100%, the totality of the environmental footprint of our buildings. And look, you can kind of do some simple math around this to understand what's the impact globally. We know currently we're building around the same floor areas as Japan. All the buildings in Japan, if you add them all up, that floor area every year. So between now, 2023 and 2060, we anticipate building the floor area of Japan 37 times. About 230 billion square meters, if you're interested in the big numbers. And we can kind of work out what the embodied carbon that will be on the back of a napkin. So on this slide, on the left-hand side, you've got the carbon budget remaining from the IPCC. This is actually out of date now, but I've kept it in. And if we want a 50% chance of remaining at 1.5 degrees, we've got 500 gigatons in our carbon budget, because greenhouse gas emissions are cumulative. They accumulate. The latest data suggests actually that's about 250 gigatons, not 500. But let's assume it's 500. Now, if we carry on building the way we're building, on the right-hand side, you can see the map. By 2060, if we build 230 billion square meters, and if we build that in the same way we build domestic Australian construction has an embodied carbon of about 660 kilograms per square meter. So every square meter we build, the detached house, it's about 660 kilograms of CO2. If we built everything the way we built our kind of detached housing on the fringes of the city, that would be 151 gigatons. So it's 30% of our total carbon budget gone just through building. Just through building houses as well. Before we've turned a light switch on, before we've taken a bus ride, before we've fed a human being. That's fundamentally unsustainable. And what you end up with is what I call the global embodied carbon contradiction. And this graph is from UNEP, and this kind of sums up the contradiction that the dots you see are anticipated floor area, how much we're going to build globally. The bar charts are how much carbon emissions we can safely afford to emit. How do we double global floor area while getting down to net zero? And that's the crux of a lot of the research I'm involved in at the moment, some of the projects that we're kind of looking at, and which I'm going to kind of talk you through. And so that's a pretty big challenge. I think don't quite have the answer yet. We're still working on it, but it is a contradiction in terms in many ways. There's been lots of targets that have come up to look at how we reduce embodied carbon. Two fundamental ones are by 2030, the suggestion that we need to reduce it by 40%. And by 2050, we need to get down to net zero embodied carbon, which is a term 2 or 3 years ago didn't even exist. It's still, at the moment, pretty ethereal term in itself as well. That's the kind of the theoretical background of all of this. I'm going to talk you through 3 or 4 projects we're doing at the moment to look at embodied carbon. They're in no way as impressive as Professor Ung's multidisciplinary kind of projects, and I'm lucky enough to not be working with too many difficult people as well, which is good, but I'm sure it will happen soon. The first project was a collaboration with Multiplex through David Prasad's CRC for Low Carbon Living, which we called Carbon Value Engineering. this project looked at what changes we can make to buildings to reduce embodied carbon. Simple changes we can make during the design stage. One of the most fundamental challenges with embodied carbon is the structure. It's a structural material. Structure is typically about 40% of embodied carbon. So we looked at what alternative structures and structural materials could we utilize to reduce this. So we simulated this as-built building. This is, I think, an 18-story building in Sydney, residential mixed-use building, 5 stories of underground car park, big underground car park made out of concrete. And we looked at several different structural configurations to reduce embodied carbon. So the building had an embodied carbon of about 750 kilograms of CO2 per square meter. If we change the concrete frame to a concrete post-tension floor, we can save 8%. We change to a steel frame and CLT floor, we can save 16%. The most sustainable or the lowest embodied carbon was a whole timber building, which we start to see the emergence of timber now as an alternative structural strategy where we can save about 26% of embodied carbon without impacting the GFA. And actually, we deal with the costing of these buildings as well. Technically, that timber building could be about 5% cheaper than the concrete building, but developers put an additional level of cost against these kind of buildings because of the innovation in them. So timber buildings tend to be more expensive, but from a fundamental materials perspective, it will be cheaper as well. And then we cranked this project up with another project, which I'm working with Will on, which is called How Low Can We Go? So we've not only started changing the structure, we've gone, okay, what else can we change? How low can we make embodied carbon? So again, we've taken a 6-story office building this time, which is the blue bar on the left-hand side, and we've started changing the building. We changed from a concrete to a timber frame building. Brilliant, you can save a little bit. Then we started changing the window to wall ratio. We changed from an aluminium skin to a timber and aluminium skin. We put straw in the facade. We changed the grid. One of the big challenges with embodied carbon is we like big grids. I think this building had a 9x6 grid to start with. So we changed the grid to a 3.5x6, much closer grid. Many more columns. Architects don't like columns. I like columns. I'm on a campaign to embrace a column. If you get a chance today, give a column a cuddle. Give it a hug. Columns are good. If we add more columns in, we reduce the embodied carbon of the floor. Simplest way you can reduce embodied carbon by adding columns. So we added more columns. The more and more and more we recycled as much material as we can. We probably saved about 50%, 55% of the embodied carbon. What's really interesting, though, is that gives you just a snapshot. When we consider the temporal nature of carbon emissions, so buildings emit carbon over their life, and we include the sequestration of the timber. So timber, when trees grow, they photosynthesize, they absorb carbon dioxide and store it as carbon in the woody biomass. But at the end of the building's life, typically that timber's burnt or it's landfilled and it re-emits the greenhouse gas emissions. If we consider that dynamic process as well, we can actually get down very, very close to net zero embodied carbon for a period of time. So the blue line, the bottom blue line, is the lowest embodied carbon building we could get. We got down to about 82 kilograms of CO2 per square meter, which is super low. And we think, I'm looking in Will's direction, we can get down to negative figures at least temporarily. So it demonstrates that net zero embodied can be achieved, but you've got to basically game the system a little bit. And there's a lot of controversy around whether timber stores carbon and how you balance that and how you mitigate for it and how you measure that as well. But that's one of the projects we're kind of involved in. Another project we do, and this is, I've got to big up my PhD student, Unique. I'm sure in the future she will go to Hong Kong and work for Edward, like a well-traveled path of our graduates. So Unique is doing her PhD on adaptive reuse and vertical extensions. So we all know adapting a building, recycling a building is more sustainable than knocking it down. It's pretty obvious. The problem we have is, you know, 4-6-story building in the Sydney CBD. That's not financially viable. People want to build a 10-story building, 15-story building. So that's why we knock these buildings down. What Unique is looking at is, can you build on top of the existing building? You recycle a building and then build extra stories. on the structure. So we've been doing some research on historical structural codes and found many buildings, particularly industrial buildings, have significant amounts of excess structural capacity. So they're over-engineered. We can build timber extensions on the top. So the diagram you see here is mapping of different vertical extensions globally, and you can see the large number of industrial buildings that tend to be built on top of, and that's because they've got this additional structural capacity. They're meant to have big machinery inside them. They get changed to residential. You take the machinery out, and you've got these big columns that can actually take extra floors. And so Unique is doing a lot of research at the moment, taking example buildings in Sydney. I think this was formerly a school, and looking at how many stories of additional concrete we could build on top of it, how many stories of additional steel, how many stories of additional timber we could build on top. So we can create new space while also reducing embodied carbon. I'll finish with a big study we did a few years ago, which asks the question, can we get Australia down to net zero? Can we get the built environment of Australia down to net zero? And this was a project which was a collaboration between UNSW, Monash, CSIRO, UTS, and others, sponsored by the Digital Grid Futures Institute. We modelled economy-wide pathways to achieve net zero greenhouse gas emissions in the Australian built environment. So effectively, we modelled all commercial buildings and all residential buildings in Australia between 1990 to 2050, and considered both the embodied carbon and operational emissions as well. And the model is what we call a top-down model. So it's not a bottom-up one. It's a model that instead of saying, hey, we're going to double the amount of floor area, it says floor area is linked to migration. Floor area is linked to wealth. So we're going to track wealth and migration, and that will, in the model, determine floor area, and that will determine greenhouse gas emissions. So we wanted to look at the feasibility of reaching net zero through that kind of model. And we use 3 different scenarios. There's a business as usual scenario, which includes higher population growth, higher temperatures, and higher resource demands. So this is if we carry on as normal. And that assumed that 30 to 50% of all buildings in Australia will be electric by 2050, 60% renewable energy to national level by 2050 as well. Then we had 2 low carbon scenarios. Scenario 1 had lower population growth. Again, remember, population growth in this model is linked to floor area. Additional investment in energy efficiency, so 80% of all buildings electric by 2050, and then 80% renewable energy in 2050. And then the stretch scenario, the fingers crossed, maybe we can do this scenario where we had 100% electric buildings by 2050, 100% renewable energy by 2050. One of the big changes we did in this as well is we cranked up the timber buildings. So we said every year there'll be an increase in timber multi-story buildings up to 30% by 2050. So 2021, 1% of buildings were timber, 2022, 2% were timber. So we really cranked up the amount of carbon storage we could embed within the built environment. This is a model, this is the results from the model. This is GDP, so it's an economic model. And what you can see in this is the big dip in 2020, that's COVID. But you can also see GDP curving when you get to about 2050. That's due to urban heat. That's due to climate change. It's due to productivity losses due to everyone being really hot, effectively. So the model is sophisticated enough to build in things like productivity changes due to climate. But more importantly, this was the operational emissions, 1990 to 2050. So you can kind of see the difference. Business as usual would have 59 megatons of CO2 by 2050, down to scenario 2 was down to about 3 megatons. So really about 95% reduction. The embodied carbon, there was a big dip in 2020. That's when we stopped building due to COVID. Then there's the rebound effect, which we're seeing now. So the model was sophisticated enough to manage those kind of things. And then what we found is business as usual was 4.3 megatons. Now scenario 2 actually got down to negative embodied carbon temporarily. And that's due to the large amount of timber buildings that were being constructed and the temporal long-term storage of carbon in the built environment. as well. And you add them together, and we got down to very close 94% reduction of emissions by 2050. And with some scenario analysis, we were able to prove that with changes to policy, we could theoretically get down to net zero embodied and operational by 2050 in Australia. Now, this study did have some limitations. You know, that reduction could be quicker. We feel it could have been made by 2040 if we built smaller. But the model did not allow smaller buildings. The model said, as people get wealthier, they buy bigger houses, which is a well-known kind of algorithm. But if we reduce the floor area, we allow people to live in more compact, kind of high-density environments, that probably would have reduced it quicker. And we didn't manage it. We didn't manage any retrofit into the algorithm either. So with retrofit, instead of demolish, rebuild, it's possible we could have made that reduction down to net zero quicker. So look, just some headline conclusions. We did find net zero whole of life carbon was possible by 2050 in Australia, but there's no silver bullet. We're not going to timber our way out of this mess, what I like saying. These are combination of measures: rapid shift to renewables, massive electrification of buildings, ambitious investment in energy efficiency, and replacing carbon-intensive materials such as concrete with timber where possible. And it's made much easier if we build smaller and refurbished more. Thank you very much.